Welcome to our next segment of this series on AI Essentials for Project Professionals. In our previous session, we established the strategic context for AI in the exponential age, clarified what artificial intelligence means in the PMI framework, and examined the three foundational elements: perception, prediction, and planning. Today, we'll explore the technical architecture behind AI. All definitions and explanations here are sourced directly from PMI's AI Essentials for Project Professionals. PMI describes AI as machine behavior and function that exhibits human intelligence and behavior. This includes the ability to perceive surroundings, learn from training or experience, make decisions, and engage in natural conversation. AI is not a single technology. It is an umbrella field encompassing a suite of computational methods. Within that field resides machine learning, and within machine learning resides deep learning, which powers today's most advanced AI systems. PMI defines machine learning as a subfield of AI that uses algorithms to learn patterns from data and optimize outputs based on feedback. Machine learning systems support perception, prediction, and planning. Some examples in project work include predicting which tasks on a Gantt chart are most likely to slip based on prior performance, or classifying stakeholder communications into sentiment categories, positive, neutral, or negative, or automatically clustering related risks in a RAID log to reveal underlying themes. Machine learning reduces the manual processing burden on project professionals and enhances decision accuracy. PMI defines deep learning as a subfield of machine learning that uses neural networks with many layers, enabling the model to learn very complex patterns. What makes deep learning deep is that they contain multiple hidden layers, each performing a mathematical transformation. This layering enables recognition of patterns too complex for classical machine learning. Some examples from project work of deep learning include recognizing architectural patterns in engineering drawings, interpreting geospatial imagery for construction progress, detecting anomalies in system logs during IT implementations, or understanding unstructured text such as meeting transcripts. Deep learning is the backbone of modern perception and pattern recognition. Now, PMI explains that deep learning relies on neural networks, which are computational structures inspired by biological neurons. They receive inputs, weigh them, pass them through activation functions, and generate outputs. With these network layers, we have the input layer, which receives raw data, the hidden layers, which progressively transform inputs, and the output layer, which produces predictions or classifications. This is the architecture behind facial recognition, audio transcription, predictive analytics, and generative language models. One of the most important concepts in modern AI is the foundational model. A foundational model is a large AI model trained on enormous data sets, which can be used as is or further customized for specialized tasks within an organization or industry. Some characteristics of foundational models are extremely large training data, significant compute requirements, general purpose capabilities, or the ability to support multiple downstream tasks. Some examples from a corporate environment include a finance-oriented model that analyzes historic budget performance, a model optimized for engineering documentation classification, or a risk analysis model trained on years of incident and failure data. Foundation models enable enterprise-grade AI without requiring organizations to train systems from scratch. PMI defines LLMs, or large language models, as a category of foundation models trained on large language-based datasets that can generate text-based content and perform a wide variety of language-based tasks. LLMs can summarize documents, answer questions, draft communications, generate plans, analyze requirements, translate languages, or interpret qualitative data. The guide notes that transformer-based neural networks excel at processing sequential information and power LLMs. Transformers introduce the concept of self-attention, enabling models to weigh the importance of different words relative to each other in a sentence. Some examples of LLMs that you may be familiar with are GPT models, Google's Gemini, Meta's Llama, Mistral, or Claude. These models underpin virtually all modern corporate AI assistants. PMI stresses that foundation models are essential because organizations can fine-tune or prompt them for domain-specific needs rather than building models internally. This includes project schedule analysis, documentation classification, stakeholder communication drafting, complex risk modeling, or monitoring and forecasting. The ability to adapt a general model to specialized context is a critical factor in enterprise-level AI adoption. So why does this matter to project professionals? AI is not abstract. It directly impacts how PMs work daily. According to PMI, AI will transform project planning, success measurement, work product generation, consumption of shared project knowledge, monitoring and reporting, and resource allocation. Project professionals must understand the technical foundation of AI not to become data scientists, but to evaluate tool capabilities, identify appropriate use cases, apply responsible AI practices, validate outputs, integrate AI into workflows, and support organizational AI strategy. Knowledge of AI structure equips PMs to lead, not just participate in, the AI transformation. In today's session, we clarified the relationship between AI, machine learning, deep learning, neural networks, foundational models, transformer architectures, and LLMs using PMI's definitions directly. In the next section, we will explore generative AI, predictive AI, and prompt engineering, including detailed definitions, how Gen AI systems are trained, how prompting works, why vague prompts fail, best practice prompt structures, and real-world project examples.